Welcome to the online causal inference seminar. Today, we're very lucky to have Bottou from Facebook, who's going to tell us about learning representations using causal invariance. Our discussant today is Dominik Rothenhäusler from Stanford. We are, please submit questions throughout the talk. We don't have anyone on Q&A today, but we will try to direct questions to Leon when possible. So submit them through Q&A. That's the Q&A box, not the chat box. And we'll do your best to answer as many as possible. So with that, Leon, please start whenever you're ready. I'll stop sharing.
So share screen. So hello, good morning. Thank you very much for having me here. This is a talk that's something that's very much in flux, meaning that there are plenty of things we don't understand, but we think it's important. And it's worked with Martin Ajowski, who was in New York University, now is a postdoc in Paris in area. Ishan is now in MIT, and David Lopez-Paz is still in Facebook. We're still working together. And to save some time, I go a bit faster on the motivation. But my goal is not typically a statistical goal. I'm interested in AI, and I'm convinced that it's not going to be possible to do AI unless we understand something about causation and about how the world works, rather than what the superficial correlations are giving. And okay, let's go. One of the hints of this problem, so everybody speaks about deep learning, it's supposed to be AI, and I have my doubts about this. And one of the problems came from this little experiment that was already quite a while ago. So the task was to detect in images what people are doing. There was a series of actions, the classification problem, and one of them is giving a phone call. You would get a bounding box, and supposed to output a label saying whether the person in the bounding box is giving a phone call or not. And we quickly got state-of-the-art correct on this data set. It was large enough to be actually significant, except that Maxime, who was doing a lot of the work, told me, it doesn't really work. So here is a row of payphones. And if you move the bounding box on the person, it says not giving a phone call. That's correct. If you move the bounding box on a payphone, it says giving a phone call. So in fact, the only thing that system does is realizing that there is a person on the phone in proximity and say, oh, that's enough, it's probably giving a phone call. And the problem is that the learning algorithm is statistically correct. When I have a typical static image data set, whenever there's an image of a person near a phone, chances are that the person is giving a phone call. It's a selection bias. Now, this is the interesting picture. So the learning algorithm is statistically correct, is missing the point. So what you see here is more than causation. It's something actually that's a bit deeper, in the sense that by just defining, taking a task, recognizing action, and saying, well, I'm going to create a statistical proxy problem to solve this task because I don't know how to solve it from first principles. Well, I'm not always solving the right task. There is a gap between the statistical proxy we define and the task we want to solve. So in the 90s, when we were using datasets, we would curate them very carefully. Like we deployed the check reading systems with datasets that were really curated to very, very close to what were the actual conditions. In the last 10 years, datasets are too big to be curated. There are data collection biases, confounding biases, feedback loops, causality problems. And the machine learning algorithms take advantage of all the spurious correlations nonstop. So the statistical problem is only a proxy, which means that the machine learning is entering what I sometimes call, the name is from Bottou, the post-statistical age. I don't know if it's true, but something like this. So what is a spurious correlation? It's a correlation that is present in the data that we do not expect to hold in future use cases. What informs this expectation? We can have substantive knowledge about the problem, or we have past observation that could inform us about this. Now, the substantive knowledge is very interesting, But it also comes from observation, because we as humans, as a group, have been able to understand these things. So there is something to understand. Now, past observation, this is in principle what's in the training data, and we know it's biased. So the first observation is that when we do some machine learning, we collect data at different points in time and space in different experimental settings. That, for instance, take a sentiment analysis task for cargo, for text, for NLP, natural language understanding. The text can come from the Gutenberg project, the text from the literature has been transcribed by hand, or they can come, let's say, from a social platform where you have little pieces of a different kind of English that can also have a positive or negative sentiment. This is a completely different process to obtain data. And who says this is the same task to start with? Anyway, we shuffle all these records, and then we pretend they are ID. So shuffling the data is a loss of information. It's important that we collect the data in a very heterogeneous settings, and we would like to find something that's common to all of them. So in this work, we follow the footstep of Jonas Peters, Dominik Janssen, and others, and we consider the data comes from a multiplicity of environments, each with a different distribution. And we have training sets for some of them. We would like a predictor that works for many of them. This is not a pure statistical problem because the environments we have, they're not random. They could be pretty much anything. There is an order to these things. So basically, we cannot assume that we have a random subset of the environments. We just have some of them. So one typical approach when you have spurious correlation, you want something more robust, is to do something that is the robust approach, where you take the maximum of the error and you minimize this maximum of the error on all your distributions. It's important to have a baseline per environment, because it might be that one of the environments is much harder than the others, and we just dominate the problem. How to adjust them is a bit tricky. But anyway, there is something pretty obvious that if you restate this problem as a constraint optimization problem and you use the standard Caron-Kuntiker results, you see that a robust regression is a first-order stationary point of a weighted square error. So basically, it means mix the environments with the right proportions, which depends on the baseline performance, the RE, and find the stationary point, and chances are that you're there. So we made progress on this theorem. We can do this now without the KKT qualification conditions, with infinite number of environments. So this is quite general. But anyway, this says that it's sort of amounts of mixing the environments with the correct proportions, which is a bit of a downer. We want something else. So suppose you have 4 distributions, P1, P2, P3, P4. If we say that all of them should have low error, that means that any convex mixture of them has a low error. So you guarantee something on the convex hull of this distribution. And this is achieved by optimizing for one of them. And this is typically what algorithms are doing. Now, there might be valid distributions outside of this convex hull. So here is an example. Suppose you have a search engine query classification problem, and you observe on several days. Most of the queries have constant popularity. Orange juice is not going to change much from one day to the next. But something like causality seminar might have increasing popularity, and something like New Year's celebration could have decreasing popularity. So that means that on successive days, you're going to see these changes in popularities, and this change in distribution. And of course, you would like something that works in the near future, where causality seminar is important, and in the more distant future, where it's gone again until next month or something like this. So interpolating between so my 4 days, oh, by the way, I forgot. My 4 days, they're here, because basically all my classification, my queries are dominated by the constant popularity ones. And on 4 different days, I see 4 points that are close to that one. It's not enough to be robust on this. I want to be robust on the whole thing. So now if I go back to the phone example, in my data, I could have different sources that show different selection biases. If I get pictures, I know that the high proportion of the pictures are going to say that the person near a phone is likely to call. But if I take movies, I could say, well, when I take a little movie snippet, I have the same selection bias. But if I take the frames in the movie snippet, most likely I have a beginning where the person is near the phone, then he grabs the phone, gives the call, puts the phone back. So I have more frames where the person is near the phone and not giving a call. So if I look at these two data sets, the one from static images and the one in frames on the movie, I see that the spurious correlation between person near phone and person giving a call changes between the two examples. And of course, I'm going to have different regressions. What I would like is to learn what remains invariant across these environments. So let's look at a strong requirement. Suppose that I want to simultaneously minimize the error in each training environment. We find a solution that works in all of them. So it's not always possible, especially when the data is noisy. And we can wonder what this means in terms of mixture coefficient. And there is something tricky, evident, is that if f star is a stationary point of each of the expected errors, well, it's also a stationary point of every mixture of expected errors for positive or negative coefficients, all the same, because the derivative of this is 0, so the derivative of sum of lambda e, this derivative is 0 as well. So that means that if I have this level of invariance, I can extrapolate. Now, there are trivial existence cases which are not so good for me, which is the noiseless case, where there is indeed the f star that satisfies everything. The realizable case, but in these cases, I don't know what to say really. The only case where I can say something interesting is when f star doesn't exist a priori because my problem is noisy. So when my problem is noisy, I can play with the function family to try to make it such that there is such a constant solution, an invariant solution. And in particular, I'm interested in functions that have the form of having a representation followed by a decision function. And I want to find the representation phi of x so that the regression from phi of x to y is invariant across environments. So that's the statement of my problem. So you can see problems with this statement. First of all, there are plenty of trivial cases. If this is noiseless, if there is a f an exact solution for all my examples, that doesn't mean anything. So that can only mean something on the problem that's quite noisy, which is a bit of a letdown. But anyway, we decide to follow this track and see where we would go. What's important to see here that finding a representation is about finding the relevant variables. In my view, when you observe an apple falling from a tree, we don't have variables. No, typically, you see in many people in causation assume that you have data that's well organized with variables that are very clear. In that setup, the only variables you have are pixels, the images, things you see. And it's not about selecting pixels, it's about, from the pixel, synthesizing what are the important variables, which are basically position and speed acceleration. And it's not a trivial transformation to go from pixels to position, speed, acceleration. It's actually quite difficult. So there is plenty of related work. The first is the connection with causation. And a number of philosophers have argued that invariance is the main element for causal inference, because to predict the outcome of an intervention, we can rely on only two things: the properties of the interventions and the properties that we assume are going to remain the same before and after the intervention. And if you look at the various methods that are proposed for causal inference, whether it's do calculus or the ignorability assumption, they're all methods that essentially tell you which conditionals can be assumed invariant before and after the intervention. Whether they're expressed because the graph has a particular shape or because there is a sub-var and ignorability assumption. is the same outcome, basically. And so it turns out that discovering invariant properties seems easier than discovering causal graphs. People have been working hard on recovering causal graphs, and finding the structure of the graph is hard. Orienting the arrows is even harder. And sometimes there is no causal graph at all. Like you have an equilibrium problem. There is no arrows there. And using invariant properties also easy, if the invariant they're ready to use. It's not clear that you know how to use the particular invariants you find to do what you want, but they're available for use without any complications. So the second thing, which was a big source of inspiration for this work, is the invariant causal prediction of Peters, Brillman, 9000, and others. And in this setup, they assume that the environment distributions results from intervention on a given causal graph. So you take a graph, you intervene on the graph in various ways, and that gives you a lot of distributions. The set of variables in the graph is assumed known, which I think is a big assumption. And the representation is merely selecting a subset of the variables. But they have essentially a set of results that say that if you find an invariant representation, you essentially have recovered the direct causes of Y, which was the target of your regression. The third one is adversarial domain adaptation. So people having several environments wanted to make classifier that wouldn't depend on the environment by essentially having a kind of classifier to measure whether you could recognize the environment from the internal state. So it's difficult to point the arrows because I have my, can you do that? Yeah. So basically you have the classifier here, and you have another one that tries to recognize the environment, and you would like this one not to work. So basically you have a dual objective. This one says, I want a good classifier, but I would like some internal features to be such that I cannot recognize from which environment comes the example. Now, if you do that, that means that the distribution of the feature doesn't depend on the environment. Therefore, the distribution of the output doesn't depend on the environment either, but that's not necessarily realistic. If you take various environments, you're not going to necessarily have the same distribution of the outputs. So it's a bit too strong a requirement. And there are variations like conditional adversarial domain adaptation that try to do this. And there are also reasons to believe that this is, again, too strong. This is too strong an approach, but it's received a lot of attention lately. And then you have robust supervised learning, or distributionally robust optimization, depends who you're talking to. And this time you do the argument of the supremum on a predefined neighborhood of the training data distribution. It can be defined by a Kullback ball, by Wasserstein ball, and so on. And basically, it all depends on how you define this set. So one approach to use invariance is to try to bias the solution of, let's say, a machine learning system or statistical system with a regularization term that favors invariant solution. And the question is, what do we put in this term? It's a bit tricky because if you take a problem like this, where you have a representation function and the decision function, and x, and you split x as relevant and spurious, invariance is achieved when phi suppresses x spurious. But it's not continuous, because if phi doesn't fully suppress x spurious, the decision function g can amplify it and restore it. So there is a discontinuity exactly where we're looking for a solution. Another way to express this is that we have a lot of equivalence classes. Like if I take an invertible function psi, and I insert psi in time minus 1 here, I have a new feature function and a new decision function, and I have the same thing. And of course, there are constraints. If I say that the decision function should be in a certain family of function and the representation function should be in a certain family, I would like phi compose psi and psi compose g to be in the proper families. For instance, if G is linear and phi is, let's say, a neural network ending with a linear layer, I can use any matrix, invertible matrix of psi, and it won't change anything. So in that case, G prime can be any linear function I want. So that was the trick. to first solve the problem. If G prime can be anything I want, I can choose it a priori, for instance, the identity, and we do not need to optimize its parameters. So basically, RMV1 was insert a frozen domain adaptation here. That's the identity, essentially. And the regularization term favors weight of the representation function, so that no environment would benefit from changing this layer away from the identity. And you can show that this is the right criterion, essentially, subject to the fact that, of course, the families of function are limited. And the example we started to work with was what we call colored MNIST, where we have the MNIST digits split in two classes, low digits and high digits, with a very high level label noise, 25% label noise. It's very high because the criterion we have, the very definition of our invariance, is based on the idea that there is enough noise so that there is no obvious solution to the problem. In addition, the digits have a color, and the way the color is connected to the label defines the environment. At training, the color tells the label with 10% or 20% error. And that means that on the training set, the color is a better indicator than the shape, but not a stable one, because on my two environments it's different. And we're going to test with the reverse color scheme. So if you train by minimizing the empirical risk, after mixing everything, if you test on the environments on which you trained, so different data, but same connection between color and label, well, it works very well. But if you train with the reverse color scheme, it doesn't work at all. So if you minimize with the invariant regularization, you get something that's far better, meaning that you have a performance that's much lower on the training environments. But when you try an environment where the color scheme is drastically different, then it works. So I have a question. How do we assume the Unison test environments differ from the training environments? What kind of assumption do we need for the test environments for the IRM to work? It's an excellent question. I'm going to come this later I'm going to come this later in the linear case to see that we had the beginning of an answer, but the answer are still problems. Okay, we'll go fast on this. Then we tried to scale up this, and we got several issues. First, numerical issues. The regularization is very non-convex, and we're going to see that later. The second issue is that the realizable problems are different. In this case, more data doesn't fix the problem, but many real problems are not like this. In fact, in causation, we often focus on situations where the statistic takes us completely in the wrong direction. The spurious correlation is wrong. But in real life, what you often have is that you have a problem where you have a very vast input, like images, a lot of the input. And the problem is to find the right variables. It's there, it's just difficult to find. And the problem that you have is that your system is going to see some variables that are easy and not see that are in fact variables that are superior even on the training set. They're just difficult to find. There was a lot of follow-up work, alternate algorithms, a couple applications to real data. Some of them showed little progress. And the benchmarking studies by David and Nishan, where they created a test bed of out of distribution generalization problems, and showed essentially that if you do empirical risk minimization and do a proper parameter search, you're very difficult to beat, even with IRM. So the painful lesson is that trying invariant learning on real problems sometimes yields a small improvement, but nothing close to our hopes. We're not there yet. So it's time to return to the linear case and do some mathematics. So in the least square case, both the feature function and the decision functions are linear. So I have a matrix and a vector. And of course, my whole system is linear, it's the product of the matrix and the vector. And I'm trying to find the matrix S so that V simultaneously minimizes the least square error for all, for instance. And because this is a linear problem, you can apply linear algebra. And this is one of these problems when you take it in the wrong way, it doesn't work. But if you take it just the right way, it works very nicely. And you can say that a vector W, which represents the whole classifier, can be written as the product of a feature function and a decision, the feature matrix and a decision vector, with the invariance property, if and only if but there is a necessary sufficient condition here that says that the weight should be orthogonal to the gradient for each environment. And then when you have this, the matrices S are all those whose null space is orthogonal to W and contains all the gradients. And if you look for the least square problem, that means that you just take the necessary and sufficient condition, and it's a quadratic essentially. And when you want to zero there, that tells you that the locus of these zeros are ellipsoids, and the invariant solutions are found at the intersection of as many ellipsoids as you have environments. Now, intersection of ellipsoids is not fun because it's disconnected and it's a very complicated pattern. Zero is always a solution, meaning that if you take a feature, a representation function that's null, well, it's invariant, but it's not very interesting. And we can compute this very exactly. And then you would like to know which of these invariant solutions is the one you want. And one way to look at it is to look at the rank of the feature matrix. And the idea is to have a high rank, because if you have a high rank, it means you're letting as much information pass through as possible while still being invariant. And from the theorem, the null space must contain all the gradients. So if they're independent, the rank of S has to be less than D minus M. This is the dimension M of the environment. But is it always the case? Turns out that sometimes you have a solution with a higher rank because the gradients of the cost per environment are linearly dependent. So basically, you have a new set of equations to say this. Sarah's question, but I think I'll answer later. So you have a new set of equations to say that the gradient of the CEs are linearly dependent. And when you add these equations, suddenly, if you count equations and unknowns, you have as many equations as unknowns. And this can also be seen as saying that W is a stationary point of lambda ECE, but the coefficient can be negative. So this connects directly to the remark about the way we can extrapolate by looking at stationary points. And in fact, you can even find the solution. If you take the minimal example that was in the paper, where basically you have x1 cos y, y cos x2, you observe x1, x2, and the invariant solution depends only on x1, you can enumerate all the high-rank solutions. So we take two environments. We solve for any nu between 0 and pi, a mixture with the coefficient cosine sine of my two training environments. We plot the cosine of the angle between W and the gradients against nu. It's 0 when the invariance is achieved. So if I plot something like this, so this represents the mixture. These are the positive mixture. What I see that the minimum is achieved. First of all, when I have negative coefficients, I have singularities, which are extremely annoying. The dot, dot, dot is the performance, the classification error in that case. And I have a minimum here. And if you look at the minimum, it's pretty much an invariant solution. And for a number of linear problems using this kind of algorithm, we recover the invariant solutions pretty well, as long as we don't get trapped in the high number of singularities. So if you go back to the problem, we had two sets of environments, the many environments we could encounter in the future, and the n we know at training time. So equation counting suggests that the only invariant solution, so if m is greater than d over r, meaning that I have a higher rank enough, the equation counting suggests that the set of solutions is discrete, and therefore the solution on E all is one of them. I didn't explain that well, sorry. I assume there is a unique invariant solution on all my environments, the large set. and I get m environments at training time in generic positions. If m is greater than d minus r, the solutions form a discrete set. So if I'm a little bit higher, I might disambiguate. So that's the idea that, in fact, maybe you can show something. And under appropriate genericity condition, do we recover a unique solution when the rank is high enough? And so we can define a proper genericity condition, which is complicated, show that indeed the genericity condition, and get the nice theorem, which unfortunately requires an additive noise assumption. So up to an additive noise assumption in the problem, you can show that indeed, if there is an invariant solution of ER, and you get a sufficiently large number, so there is a general solution of rank R on ER, and you get a sufficiently large number of environments for training in generic position, you can solve and you're going to recover the solution. Sort of nice. Alas, there is a problem. If I take my proxy of my NNIST problem, which is this, so this I'm epsilon 0, epsilon Bernoulli, then -1 + 1 with various probabilities. When epsilon 0 is 1/2, these two problems are equal. So it's a simplified model of color NNIST, and there is no additive noise there. So the theorem doesn't apply. And Kamath, Angela, Sutherland, and Srebro found a counterexample. And in fact, by using the necessary insufficient theorem, I can compute the solutions. If I take these problems, all the ellipsoids pass through 4 points that only depend on A. I have the degenerate solution in 0, which means the representation is 0 that I knew. I have the true invariant solution, and I have two spurious solutions that appear when A is greater than 1/√2. That means when the noise is low enough. The threshold for the noise is something like 15%. So in the color NNIST, we had 25%. That was okay. We had noticed that when you reduce the noise, we cannot do it right anymore. And we thought there was an optimization problem, but in fact, no. We are just recovering these spurious solutions. And then you can look at how the spurious solutions change. So depending how you set B, which is the string environments, they may or may not have a lower average error. So sometimes we avoid them. And small changes can change everything. Like you add the bias in the linear decision function, and you get completely different setup and a completely different results about the presence of spurious points. There are still spurious solutions, but the conditions for the spurious solutions are extremely fragile. But what this suggests is that you have an adversarial relationship between the two families of functions. If you have a large family of representation functions, you have more opportunities to fool the classifier into being similar, having the same optimum across environment. And if you have a large family of classifiers, you're going to detect differences between representations. And when everything is linear, you're just below what you would like to. So of course, what you can do is, okay, instead of having G linear, make G 2 layers of a neural net and try to make it work. And then you get into optimization problems. Anyway, the conclusion is the following. One, for machine learning, for AI, the statistical problem is only a proxy. It's a nice way to address our problem, to define a proxy problem that's statistical we can solve, but it's only a proxy, and we should investigate how this proxy relates to what we actually want to solve. The second one is nature does not shuffle the examples. We shouldn't. The third and fourth one is that invariance across environments buys extrapolation power and captures a lot of causation. There is some evidence that this can work, and we don't know how to achieve it reliably. Even the linear case gives us trouble. So that's the end of my talk.
Thanks, Leon. Maybe we can answer this question from Sarah Magliacan, so I can read it off. It reads, is the assumption of trying to be fully generalizable doomed to fail in the case of latent confounders when not even causal parents may not be enough? Would it make sense then to exploit at least some of the unlabeled data in the test domain, similarly to semi-supervised learning, to check what kind of shift is happening, at least in the features?
The answer is yes, it will make sense. Another answer is, well, I'm starting to doubt that that for many machine learning problems, not statistical problems, not medical problems, for instance, but for many machine learning problems, I'm starting to doubt that the confounders are completely hidden. I believe that you often have a very large dimensional input data with a lot of information that we don't know how to exploit. And the confounders are there, they're just hard to find. It's hard to find the function that changes all these pixels and retrieves the data. And if you think about the scientific process, how people looked at a scientific problem and eventually discovered the confounder, it's not that the confounder was not accessible to them, it's that they hadn't found how to express the confounder from all the data that was available. And when they start having hints about the confounders, now they can go and look for it. They can take a microscope, they can take, and when they found it, they have it. Sarah, you shouldn't be scared. I'm seeing the chat.
All right, well, thanks for the great talk. Maybe we should move to Dominik now for the discussion. So Dominik, feel free to share your screen and start whenever you're ready.
All right, thank you. So first of all, thank you so much, Leon, for the very nice talk. All right, so the discussion here, I'll have here, first of all, a disclaimer here. This work, of course, touches a lot of different issues. I will now focus mostly on the conceptual aspects that relate to causal inference, because that's what I know the most about. There are lots of aspects related to like that this is a hard optimization problem, also how you can generalize in nonlinear models, which are very tough and that I will not touch on here. Okay, so the motivation, I'll go over this very briefly. So as discussed by Leon, machine learning models can fail under distribution shift. So what can we do about this? And one way to think about this is like to go to causal inference and realize that we have a very nice invariance property there. This was realized a long time ago, but has become a lot more popular recently. So essentially, if you have a causal model, meaning that if you look at the distribution of y given its parents, it will be invariant under interventions on covariates. Important restriction here is if there are no latent confounders, but at least from this perspective, if you know the causal structure, you will be able to make predictions that generalize very well across certain perturbations on your distributions. You can also reformulate that a little bit under the additional assumption that the noise is additive, in which case you can show that causal predictions I define here as y given do x equal x. So if I intervene on all the covariates, causal solutions solve a minimax problem where the supremum is taken over all distributions that arise from do or shift interventions. So in some ways, causal solution here are also just solving minimax problems. So if we just care about doing robust predictions and we want to protect against a certain type of distribution shifts, sometimes the causal solution is the optimal one. Okay, so this somehow motivates, at least if you directly start from a causal perspective, to say, well, maybe we want our method to understand some aspects of the causal causal system. Okay, so now we could say, well, okay, let's just like always use this the causal mechanism. So let's always try to like strive the fully causal solution. And there are a couple of issues with that, and I'm happy to discuss if people feel differently about that. But generally, there can be some downsides with going fully causal. The problem is that, first of all, in practice, it's incredibly hard to obtain. We all have some experience with that here in the online causal inference seminar. The causal solution can actually have overly conservative predictive performance if we go back to the causal model here, the causal model solves a minimax problem where the supremum is taken over all kinds of interventions. Maybe on the data set, we only see interventions in certain directions or on certain covariates. In that case, the causal prediction might be overly conservative compared to what we want to generalize across. So that's the second point. Third point touches what Sarah has said. Actually, this result above only guarantees that causal solutions are robust with respect to interventions on covariates. If you have perturbations on confounders, then these kind of causal predictions can actually be quite sensitive and fragile. So depending on what you try to protect yourself against, sometimes you want actually a causal, you want actually to make a causal prediction. Sometimes you want to make anti-causal predictions that can be more robust. But in any case, what you do want probably in these settings is that the prediction in the end respects some part of the causal structure of your problem. Okay, so now the question is, are invariant representations a healthy compromise somewhere in between? So we move towards causality, but we don't go all the way usually, because in most cases, your environments will not span all the perturbations that you could do on the system, but only certain parts that you might actually care about. Okay, so what's the proposal here? Leon talked about that, so I'll just quickly recap. So we're looking at, we want to try to find a data representation phi such that the minimizer is invariant across data sets. So phi is now just a function of the data. And now we try to find a phi such that from that perspective, from that representation across all environment, we fit the same model. Now, if you stare at this a little bit, you're going to realize this is a very challenging non-convex optimization problem. I won't get too much into that. For quadratic loss, it simplifies a little bit. In that case, we just want to find a representation so that y, given the representation, is the same across data sets. And then we try to find the representation that minimizes the overall error. All right, so to give some intuition, I'll look at one particular example. It's actually, first benefits. Yeah, so what I really like about this is that, first of all, it's a general principle, so you can come with your risk functions. This gives you a very general way of penalizing towards invariance. The nice thing is also that I believe that it moves somewhat towards understanding or incorporating the causal structure of the problem, but not by going all the way to causality and making it overly conservative. So you only try to intuitively protect against the perturbations that are that change between settings, but not like against everything, which might actually be impossible. Also, a nice thing, it can deal with latent variables, and we don't need much knowledge about how the environments are generated, so we don't have to have much background knowledge. Okay, let's get some intuition. So this is actually an example that's in the paper, but I want to kind of carry this discussion a little bit further and see what we get. So here we have x1 has a causal effect on y has a causal effect on x2. So x1 is drawn from a Gaussian with varying sigma squared, and y is equal to x1 plus a Gaussian with varying sigma squared. And then x2 is a function of y with a Gaussian with fixed variance. And now we assume to have a variance perturbation. So across environments, the variance of these two variables here change. Now, the first thing that you might try to say, okay, I want to do a regression of y on x1 and x2. You're going to realize very quickly that's not an invariant representation if you change the variance a little bit. Okay, so now in the paper, they discussed that x1, if you just take the parent here, will actually lead to an invariant representation. So now, okay, that looks like success. We have invariant representation here. Now, what I realized when I looked at this a little bit longer is that while it is an invariant representation and while it protects us against arbitrary interventions here on x1 and x2, because it is the causal solution, there is actually another anti-causal prediction here that also has some favorable properties. So the problem with X1, the invariant representation problem, the invariant representation is if you draw the risk across sigma here, what's going to happen is that the risk is going to grow quadratically in the variance. And the point here is that essentially here the residual of your y is a Gaussian with a sigma squared. So if you across environments increase sigma squared, of course your error will go up. Okay, so there's another solution that is essentially anti-causal, which is a non-invariant function, just x2. If you use that for prediction, then these changes in the variance will cancel out. And what you will get is you will actually get constant risk across these variance perturbations. This has different optimality properties than what Leon discussed. This will not be optimal across any types of interventions on x1 and x2. But what it will have is for any types of variance interventions of this type, it will have constant risk. So if we look at this plot, this is so this here is maybe the invariant one in terms of invariant risk minimization, and this one is in terms of, and this is the non-invariant one, non-invariant in Leon's language. So I think it really depends here kind of what you try to protect against. But the important takeaway is that IRM solutions will not have always invariant risk, even in cases where invariant solutions exist. But overall speaking, those two solutions just have very different optimality profiles. So it's not entirely clear to me kind of when to choose which over the other. And I think that would be very interesting to hear whether you have any thoughts about that, whether we should there are different ways we can enforce this invariance. We can enforce invariance by looking at representations, but we can also enforce invariance by saying, okay, we want risk to be constant or these kind of things, or residuals to be constant. All right, now just a few other high-level remarks. And just before I start, a quick disclaimer. These are mostly things that popped up in our research related to this problem, and they might have actually not appear in the regime that Leon is looking at, because I have never worked with pictures. The general point that I'm trying to make here is that tuning such invariance penalties can be challenging. And the high-level idea is just you can think about invariance penalties as buying insurance. And so, for example, you will have a house and you want to try to protect yourselves against wildfires. Okay, so you now try to get invariant, or you try to be robust against wildfires. Well, first of all, you have a fixed cost, and the insurance will only pay off if the perturbations actually happen. And you should, sometimes it's important to know how large these perturbations will be, because if you try to protect yourselves against very large wildfires, the cost that you pay for trying to protect yourselves against these shifts might be very high. So so you do generally want to know how large will the perturbations be in the future, so to avoid to be overly conservative. Okay, the second part of this is, let's say we now protected ourselves against wildfires, and maybe to protect yourselves against doing that, your house was now built close to the water, and what that means is now you increased your risk to something else. And something similar we also observed in our case, where when you try to protect yourselves against some perturbations in some directions, and that is successful, sometimes you increase your sensitivity with respect to perturbations in other directions. So the important thing here is that you cannot just try to protect yourselves against all kinds of things. It's also important that the things that you protect yourselves against are not too different from the perturbations that actually happen, or otherwise you might have just increased your sensitivity. Now, just like a little caveat here, we usually looked at problems where the perturbations have approximately a similar dimension as the dimension of the predictors, in which if you have high dimensional problems, buying insurance is a bit cheaper than in the low dimensional settings. Okay, but that's just as as a remark here. Yeah, okay, so this is a critique of like striving for invariance and trying to protect yourself against distribution shifts. But like, obviously, if we don't buy any insurance, it might be actually much worse and our model might fail, depending on what's going to happen. So this is a tough problem, but ignoring it might also not be the solution. Okay, so that brings me to the end. First of all, I think this is very intriguing and interesting work. So I have some questions here. I think in practice, it's very crucial on how to tune invariant risk minimization. And for that, I would like to know, maybe Leon has some experience with that. How did they do that? They do like leave one data set out cross validation, and did they just push the variance penalty, the invariance penalty all to infinity, and that worked very well for them in many applications. Another one is related to what should you protect yourself against exactly? So how do we exactly choose the environments that we try to protect ourselves against? Because if we protect against the wrong things, then again, we might get conservative performance. The third one is related to that. I'll skip that for now. In the data set that you looked at, you had a relatively low dimensional perturbation. You only changed the color, but you could imagine that in real world applications, a lot more things change. So I was wondering whether you have some experience, whether this also works for higher dimensional perturbations, if actually a lot of things change between settings, in which case you probably need a lot of environments, which then might get unstable. Yeah, last but not least, yeah, if we have additional background knowledge, then maybe this whole optimization problem gets a lot easier. So for example, if you know that only certain things are perturbed and other things are stable, then maybe you can change the penalty a little bit. And yeah, I was wondering whether Leon has some thoughts on that. Anyways, that's all from me today. Yeah, thanks very nice for the nice talk. And yeah, really happy to hear if Leon, you have any thoughts related to that.
Thank you, Dominik. So yeah, Leon, maybe take some time to respond.
So there was an interesting comment about the constant risk solutions. But if you take that example, you notice that it's a constant absolute risk, but not relative. When you change the sigma, you change the variance of the y's. So it's the same risk relative to numbers that can change widely in range. So I think you're reaching the limits of the little example there, because it's in the end, the constant risk solution is very related to the kind of environments you consider. In my viewpoint, my viewpoint is not a statistical viewpoint, it's kind of an AI viewpoint. I'm looking at the world, I want to understand how it works. And if I'm looking at the 3D scene, well, there are objects, there are things I can move around, there's actually a physical reality that's pretty clear. And if I find it, then it should be good. It's not an insurance. Trying to find that you have objects you can move in front of each other, and there is the things you're looking at actually correspond to a projection of 3D space, which is not an obvious thing. It's something to be found, and once you found it, you got it. So this is why I'm very annoyed by the fact that the IRM criterion demands noise. Now, recommendation how to tune IRM in practice, size of the perturbations. You mean the environments, how to choose the environments. For a statistical problem, I can't tell you. For a real problem like an AI problem, I believe that when you get data, if you be careful about where the data comes from, you're going to see environments, and they're relevant. But temporal consistency, for instance, gives you a lot of information. Location gives you a lot of information. Low dimension perturbation versus high dimension perturbation, that's a problem. The way IRM is described, essentially, you need one extra environment to remove one extra dimension from the spurious feature space. Now, if you say that your space is a bunch of pixels, you have millions of them, you're in trouble. can you incorporate background knowledge about distribution changes? I guess my bet is that it's possible to do via the selection of our environments. In particular, there is a simplified case, what people call the self-supervised learning these days, where in fact, you know the environments because they correspond to transformations of base patterns. Like for instance, you have images, you transform them by shifting them, changing the lighting, making changes to the image that you know shouldn't change the class or the label. And that gives you, each of these change gives you the different distribution. But it's much easier because you know the perturbation, you know what is the base image, and you know which images are related. So you can do things where, for instance, you take a particular image, you transform it in two different ways, then you run your system and you ask that some representation layer has a value that's the same for both branches of your system. And that works quite well in practice. The problem is much easier because you know this correspondence. But a lot of the recent advances in actually NLP and vision comes from this simple idea. Finally, I want to go back to the latent confounder problem. So in causation, the latent confounder problem is the poster child. The Simpson paradox is the poster child. So let's take a typical medical step. You have context, which is symptoms, patient, hospital. You have treatment, you have outcome. And of course, we know that there are plenty of latent confounders about the selection of treatment. Like doctors might say the treatment based on things you don't know. But in fact, it's not true that you don't know them. The truth is that you have all these medical records, they are a big mess, out of which you selected a couple of variables that you call context. And then you have a latent confounder problem. But why do you know you have a latent confounder? Because you went back and you found, oh, they only gave that treatment to people who had an easy problem. They only gave that treatment to people who were hopeless. So my problem really is to see the whole mess of the data and find what's important. Because this is what we expose in the real world. In the real world, we as humans, we receive a lot of inputs. And they're not summarized by just a couple numbers. We summarize them by a couple numbers, and sometimes we're missing an important one. But somewhere in that bunch of inputs, you have very strong hints. Except that we can't find them, it's too large. So the problem that you say about low-dimensional perturbation versus high-dimensional perturbation is a very serious one. You have a very high-dimensional data that comes as a mess. And in fact, in a statistical system, the human is part of the learning. Some human, based on substantive knowledge, select context variables. And later they discovered, oh, something was missing because I have a paradox or I have a confounding problem, and I have to go back and find a new one. So the human is part of the learning loop in a way that I would like to understand. Now, if you look at the whole process, not just the process of the statistical and causal inference, the whole process where you have the statistician and the person who goes into the data and actually finds, oh, there was a confounder, sorry. If you look at this whole process, there should be a source of information that allows us to do this. So if this is about understanding how we do science, essentially, because the scientific process is actually an important example of this. We do this back and forth between a big volume of data in order to find the confounders that we didn't have. It's very rare that they're really not there, and you have to go back and collect a new set of data with this new thing. Usually it was there in one way or another, right? Anyway, I thank you very much for this discussion and the way it brings a lot of perspectives, and it shows that we're still in trouble. You know, it's very frustrating because whether you look at this as how ant colonies can learn things, you know, C. elegans can learn things, and we have no idea how, which is very annoying.
Right.
Thanks, Leon. Yeah.
Michael,
Dominik,
should we?
do you have something else?
Should we take another question from Q&A maybe?
Sure, yeah, if you have
Leon
time,
has
you can
another-
take 1 or 2 questions. So, okay, so here's a question from Sarah Magliacon again. It reads, is it really necessary to learn a representation phi x, or is a feature selection method enough since we already learned a function g on top of that? So would you say that IRM is really learning a causal representation, or is it rather more a causal feature selection method?
Well, the example I have is typically the example you have an image and you're looking at the physical phenomenon. The physical phenomenon will depend on things like coordinates, measurements, positions, masses that you can estimate more or less directly or indirectly, and not the pixels. Measuring the position of, let's say, a ball in a field from the pixels is not trivial at all. This is not a linear transform. This is something that's extremely nonlinear. If you try to train, let's say, a neural network, even a convolutional neural network, to output coordinates from an image, it's actually extremely hard. No, sorry. It's in fact extremely hard. So I don't think that you can solve this problem by selecting a couple of pixels. You have from the pixels to invent a nonlinear transform that's going to give you the information, the small number of variables that are relevant to the physical phenomenon, like position of the apple, speed of the apple, all these kind of things. So it's not just selection.
I see. Thanks.
In fact, if you go back to the example of the medical problem where you have a masses of medical records and somebody has been working to select a couple of interesting variables. First of all, how do you select the interesting variables? Well, you can have substantive knowledge, but it comes from somewhere. And second, the problem of latent confounder often comes from the fact that its set of variables was incomplete. So that's a difficult step that we do by hand right now. We don't do at all.
Great, thanks. Maybe we should wrap up now. So thanks, Leon, for a great talk. I'm gonna share my screen.
Yeah, thank you very much.
So next week we have Hito Imbens, and he's gonna speak about using experiments to correct for selection in observational studies. We're very much looking forward to that talk, and we hope to see you there. Thanks.
Thanks, Leon. That was very interesting.